So if you recall, we were looking at the ridge regression, right? So ridge regression was I had beta hat, or it's like theta hat lambda is like argmin over theta, x theta minus y plus lambda theta norma squared. And we want to see what this regularization does. And this theta hat lambda times x, you saw that this over this is basically taking the samples of the function, which is our estimated function. And this guy is like samples of f star. Another way of, another way, but it's just basically 1 over root n f hat of x1 up to f hat of xn. So what we're doing here is we're comparing the quality of the estimated function to the actual function. Okay, and we saw that we can evaluate this like sort of expected, like conditional expectation of this empirical L2 norm, and it turns out to be this. They had to have this simple expression if we express everything in terms of the SVD of x. So there is a lot of like insights here, which unfortunately we can't go over, but I just want you to show you some simulations to see what this actually tells you. The main idea is that there are two components here. One is the bias and the other is the variance. And the usual least squares regression or usual linear regression, if the model is well specified, which means that the actual function is linear in the covariates that you specify, the features you specify, this term would be 0. Because you said lambda equal to 0, you can see it goes away, the bias goes away, you have the variance. One question is that why do I like include this? So why do I, because if you add lambda here, this is going to be non-zero in general. And so if you remember where this comes from, this is from the bias. So you introduce the bias, you would say, okay, this is an additional, everything is non-negative here, so everything is to the power 2. So this is an additional non-negative term. So why would I want to increase my MSE? Error. And the point is that once I increase lambda here, so this is going to get bigger, but this also gets smaller because of the lambda. If you increase lambda, you can see that this goes down. So the variance goes down, the bias goes up, but there might be a better choice than 0. So you might be able to trade off some of the variance for the bias. In the limit, when lambda goes to infinity, this is going to be completely 0. It goes to 0, but this is going to blow up to infinity. So that's why you like introduce this parameter, gives you flexibility to choose a better point, a better bias variance trade-off. It's very similar to the bandwidth idea. So is the idea sort of clear? I just wanted to show you what it does. Creating training data here. Let's say I'm doing 2 features. So this creates it's actually a single feature. So 500 and trains 500 samples from a univariate feature, and then this is random, like uniform. So 2 times this minus 1 generates something in -1 and 1. And it has to be corrected. So just -1 and 1. Alternative is to generate from a normal distribution. But let's try this. I do that, and I sort these values. And then here I'm creating polynomial features. So this is how you do it, like in scikit-learn. But let's say I'm going to do 5. So what it does is that it applies so this transformation to x. So x is like the shape is let's see, the shape is 500 by 1. Once I do this, let's say degree 2 polynomial, for example. If I do degree 2 polynomials, it adds the feature which is degree 0 polynomial, which is 1, and then x and then x squared. So if I do this, and if you look at the shape, it's going to be 500 by 3, and then you can verify, for example, that the first one is actually 1, The second one is like, again, the difference is 0. So the second one is actually x train, right, x. And the third one is x squared. So this matches. And if I do like 5, you get all the monomials of degree up to 5. So 1, x squared, x to the third, and so on. So you get like 6 here. Right. So I'm generating these polynomial features. And then I'm also like standardizing. This doesn't matter much. And here I'm just taking there are 5 polynomial features, but I'm generating the true signal from the first 3. So 1 x squared. So theta true is like this, and then concatenated with 0. So it's going to be like, so theta true would be, right, so this, there you go, understands what it would be, which is very impressive. So basically I'm padding it with zeros. So when I multiply this by that basis, so it just kills the higher order polynomials, like 0, 1, 2, and then 3, 4, and 5 are going to be 0. So the actual function that I generate the data from, so you can see here, x times this, and then I add noise. So this is going to be the true function. These are the samples of the true function. And then I add noise, and this is my noise level 3. And then I'm going to plot this. Okay, so plot this, you can see. So these are the, so I'm plotting the true function here in red. So that's the degree 2 polynomial. And then the y trains are like random, like noise level 3, so pretty like scattered around this. Okay. And the power of statistics / machine learning is that you can recover this curve because we have 500 samples, although like the things are all over the place. Even though I'm using like a degree 5 polynomial to fit, so I'm going to fit to the entire x. So the way that I'm going to generate the ridge regression is by fitting to the entire x. So if you recall what ridge regression, the way that we wrote down the estimator is via this covariance and cross covariance matrices for simplicity. X transpose x divided by n. I invert it like plus lambda I, so that's what happens here. So plus lambda I, and then invert it multiplied by cxy, which is the cross covariance. So this solved ridge basically, which by the way, like this co-pilot wrote, he knows about ridge regression, does that. So he wrote it like an earlier version, but to tweak it to the later version. But so this is like this sigma plus lambda I inverse times sigma xy. And so that's the theta ridge regression. We solve it, let's say for regularization parameter 0 here. And I'm printing the theta ridge and then form the ridge regression estimated. That's like those are the samples without normalization, f ridge. And I'm plotting the true one and the estimate. Okay, so I have to define this. Oh, and I also plot the CX, this is like sample covariance matrix. So you can see it has this nice, these are the polynomial features. So it has this nice checkerboard. So you can see this is like the green one is the fitted ridge regression with degree 5 polynomials. You can see there's a bit of wiggles because it's like better, like can fit more than degree 3, but still like close. And then this part, I'm not going to go over the details, but this is basically calculating that expectation once by simulation, expected error between the true signal and the like the f star and f hat, basically f hat of ridge by simulation. So this is going to verify our formula for us. So I'm going to do like 550 repetitions. And I'm also like I'm going to vary the regularization parameter, that's lambda, in a range. And so if you do that, that's our regularization sort of curve. And here I'm going to plot the actual one, the real one. So not the real one, the one that we calculate. So this is the value that we calculated. So here I'm doing the SVD. If you do the SVD, you can find the U and this S and V, that's actually going to be V transpose. S squared is that mu that we define. Basically, I'm just writing that formula. So this is going to be the bias term, and this is going to be the variance, exactly the formula we had. you can go through the details, and the C is like the U transpose times F star true, everything exactly as I had there. And when you plot it, the theoretical MSE, like this is the average over 50 curves, is close, sort of. But you can see the key point here is like the, although you're not using that much, like degree 5 versus degree Q, there is a slightly better values of numbers. So that this the smaller, like here it's smaller than at the origin. And the origin is the OLS. Okay, so if I, for example, go higher here, how can I go higher? So if I do, for example, so this is 10 to the -4 to 10 to the 0. So that's the range of the regulation parameters. So you can see, like, if you increase the regulation parameters, I think things get a lot worse. So good things happen very close to here. Okay. And so this is like going to match our theoretical balance pretty nicely. Okay. And I should say this is average. So if you do it for one example, it's not going to be exactly that, but like average or 50, that's like the expectation. Or the random. So this matches. So you can see there is a little bit of so at this point, like the 0, you have a certain MSE, here slightly better. Okay, so if you regularize, you get a little bit better. So if I, for example, do I don't know what that value is, but this is our like unregularized. So this is regularization 0. Let's say if I do 0.05, let's see what we get. So you get something which is much closer. Okay. So although I'm using the entire like degree 5 polynomial basis, but by a bit of regularization, I can sort of get the wiggles down. So this is sort of tells you how like it's not obvious how it takes care of complexity, but sort of takes care of the variance. Although you're using the big basis, like bigger basis than the truth, you can sort of like avoid the wiggles by increasing it. If I increase it further, it's not going to look as good. So it's still good. Like 1, you can see it starts to like you're going to pay the bias price. So it's going to start to flatten out. So if I do 10, you can see like it starts to really get flat. So it's much more smoother, but like there's a big bias. Okay. So there's optimal value, which sort of by eyeballing that curve is like around here. So this seems to also perfectly recover. And it's like amazing that you can recover it. So you don't see this red curve, you just see the blue ones. And with a bit of regularization, although you didn't get the actual degree of polynomial, you like basically use a bigger basis, sometimes called not overcomplete, but degree 5 polynomials, you get that. Is it sort of clear? Okay, it might become a little more clear if I do like degree 25. So I'm going to do degree 25 here. Like all the polynomials of degree 25, sorry, all the like bases, like monomial bases, 1 x squared x to the third up to x to the 25. So you get 26 of them. Still, I'm going to use the same. So this line is not going to be true, but I'm going to use the first, third 3 basis functions, like the quadratic part, to make the true one. The rest are going to be 0. So the actual true function is going to be still this, right? We haven't changed the true function. This one is going to look like that because the x now, the basis like has 26 columns. And if you like want to like look at checkerboard, like using that, that's one way of doing it. Now, if I solve it with degree 0, like this is 0 regularization, you can see like I'm now going to get like this is sort of overfitting. So this has a lot of degrees of freedom, so it just picks up a lot of variation. Okay. In fact, if I do later, I'm going to do like maybe if I do, for example, 25 points, I'm going to perfectly interpolate the 25 points. But this is not really ideal. Okay, so it has a lot of sort of wiggle or variance. So if I do now this, you can see like the turning point here is like moved a little bit. So maybe do it with the 0.5. It's like you can see the actual like critical part. So this saying like at 0, we pay a big price, like 0.2, but near like again 0.05 is a good like, range. So if I do that, then you would get, so let's do like 0.5 here. So you can see you get like closer, although it's like slightly bad at the endpoint. Let's do this. Yeah, it doesn't help that much, but oh, what did I do? Did I delete it? Yeah, okay. Maybe like 0.03. Yeah, I'm gonna pay a price there. In any case, you can play with this, right? Too much regularization, you start to pay a bias like issue with the like get away. So too little. So this is sort of overfitting. The idea of overfitting. Oh, why does here we do this? Okay. Every time you do it, so at the boundaries you get like worse. But if I do a little bit of this, you alleviate this a lot. You alleviate the issue. Still at the boundaries a little bit problematic, but you can see what regularization does. Goes from this to something like that. Okay. Sort of. Yes.
If you use lasso, would it be able to perfectly?
That's a very good question. So I should try that. That's a good point. So if you can recover the actual basis, the issue with the lasso is that this is a very high, like highly correlated design. You can see here, like all of them are correlated, and lasso has a lot of trouble picking up the true covariates if there's a lot of correlation. So if your design was like this is covariance matrix of the design, if it was diagonal, then it would have been like rather perfect. But in this case, my guess is that it's not gonna like find the right. So out of the 25, you want to find the 3. But my guess is that it's gonna have difficulty. It's gonna have some other parts. But it's very good to try. I haven't tried it. So the lasso would replace that L2 with the L1. If you L2 squared with L1. That's what a statistician really like. Machine learning people, not that much. They use the L2 regularization, they call it weight decay, and it's like prevalent. But you can see that lasso, like sometimes if I recall correctly, so as far as prediction goes, the regression oftentimes does better than lasso. Lasso is usually for most of them, but I don't know what it does here. It would have been very nice to actually do it. So as an exercise, you can try to do it. I don't have like more exercises. I have spent my exercise budget, but this is a very good exercise. Try lasso and see if you can recover the true function better.
I was just thinking, it's able to zero out terms.
Yes, but the thing is that that's of the issue. The thing is that you can see from the correlation, the base is like, this is like the correlation of let's say the 5th one with everything else. So with every other basis, it has a high correlation. So if it picks tries to pick 2, it might also take like maybe 6 and 8 and so it's gonna have trouble. This is like sort of multicollinearity between C100C. But these basis functions are very correlated because like x squared, x with the paired x and x squared are correlated. Like you can see like the one of them is signed, the other is not. So for example, x squared is correlated with x to the 4th, but like correlation with x to the 3rd is 0 because that was like that has a sign, right? So the odd terms are correlated with each other, the even terms are correlated, and so you're gonna have a lot of trouble picking which one. I can like substitute x2 with x4 and don't pay much price. It's a very good question. I actually had thought about doing it, but I've forgotten. And we haven't talked about lasso here, so maybe in a different course, maybe a different time, second like iteration of this course. But as an exercise, try to do it. Like this is posted online, so you can go and you can try to do gradient descent to solve lasso, but it's not efficient. And because of the fact that it's the penalty is non-differentiable, you might run into issues. I guess this scikit-learn, these guys should have like some way of solving lasso. So from the regression part. So look into that and then try to fit the like lasso and compare. We can't get a closed form solution for the regression curve, but you can do this calculation. Like this you can calculate the empirical regularization curve and then compare. Plot that against this and see. You can also do this. Good question. Any other? Very good question. So the other question. Okay, so maybe one more. I also have some sort of like a demo here. This is also nice because I believe you can. It's a very nice simple thing that like ML people like to write demos on this thing. And I tried and it worked really nicely. So let me show you. So there's like a little bit of this package Gradio. You can like introduce a little bit of code, just a little bit. And it allows you to like manipulate. So I can now, for example, change the degrees. You can see what happens if I change the degree of the polynomial. The fit sort of gets. This is for the Gaussian case. So unfortunately, yeah. So if you increase the noise, you can see like things start to like behave very erratically. Because it's Gaussian, you're going to pay a lot of price there. So I wish I had it for the. Yeah, we can change it later. The one that I want to show you is this one, which is just the regularization curve. You can see. So that's our curve. So let's do like the max lambda. So you can see if I change the noise level, you can see like the optimal. Okay, let's do this. You can see the optimal value like starts to move, right? Gets closer to larger. It becomes like larger. So the optimal choice of lambda becomes bigger. Right here, you have to increase this. You can see like it's around 0.1 now. And also, if I reduce this, if you reduce the noise, you can see like basically no regularization is fine. So at low noise, not much regularization is needed. But even if I have low noise here, if I now increase the degree, see what happens. Still okay. You can see like the prediction is not that bad. But now if I like very sensitive to noise, if I increase the noise, you can see like things quickly become problematic. Okay. Like now you're overfitting a lot. You see there's like degree 19, noise level 5. If I do like with no regularization versus a little bit of regularization, I can get like a lot of improvement in performance. Keep increasing it, you can see like at some point it becomes a little bit flat. So here really you can't predict, but you can do a lot worse than this. But, so that's how things work. Okay. So low noise, you're fine, sort of, but introduce a little bit of noise and you have a lot of overfitting. Sounds good. You can play with this and also implement the lasso. That would be very good. So this is for the Gaussian noise, and it's a little bit different because Gaussians are centered. Okay. Questions, comments? Oh, okay. One more thing I wanted to show you. That you can interpolate perfectly. How do we show this? There. See, I'm not sure if it's going to work, but let's test. Like 25, 26, let's say. And then I have 26. It may not be invertible. Okay, that's the true function, a little bit of like data points. This. This is okay. A little regularization. Zero regularization. Yeah, we can't really over. You should like interpolate, but sort of. So you can try to figure it out. I think I don't have enough resolution. In any case, check this out later for yourself. See if you can like, by increasing the point, at some point, it's going to be hard to invert. But yeah, I'm not sure that. If you have more data points, you can't interpolate, but you can see like tries to interpolate. Okay, any questions? So this is a setting where it's very easy to understand everything. So you can like write down everything in like closed form sort of, and play with things and gain a lot of understanding. So for example, you can like see for yourself, go see what the effect of the decay of the eigenvalues. So the eigenvalues of or the singular values have an effect, how fast they decay. And that KC has some effect and so on. So this was our roadmap. So the things that we covered. So hopefully you have a nice understanding of what regularization does. We have seen like different kind of regularization. One is like via the bandwidth, like a single parameter in the local averaging estimator, the number of nearest neighbors, and also regularization via adding a penalty, ridge, or lasso. We haven't seen lasso really, but you guys seem to know. There are other ways of doing it, which we haven't covered, like not optimizing to completion. You have seen like glimpses of this. So if you have a very good optimizer and you have an like a big deep neural network, you can like overfit, and you can see that if you don't optimize as well, our optimizer with momentum, for example, did a worse job than Adam in one of those, and the decision boundary was less sharp. So a form of regularization is like early termination of gradient descent. There are different kind of regularization. Early termination of GD, there's like implicit regularization in gradient descent. So this is what people talk about. The gradient descent has some sort of regularization effect itself, which we haven't talked about, implicit. But we have seen some form, and hopefully you get an understanding that. So regularization generally is to combat overfitting. And it really matters when you have noise and a complex like a model. Implicit regularization. So you've seen neural networks, we see more deep learning hopefully today. Feature maps, we have seen basis functions. This, if you continue, leads to the kernel idea and kernel methods, which we unfortunately don't cover. SVMs are close. Relatives of logistic regression. Basically, if you change the logistic loss to hinge loss, you get the SVM, like soft SVM. There are like better ways of motivating why you should do that, but they're very close. Bigram language models, GPT, that's what I'm going to talk hopefully today about. Ensemble methods we haven't covered. And I don't think I can cover, but random forest, gradient boosting. Read about these for yourself, please, so that you know about them. These often beat neural networks on tabular data. So these are the state of the art for tabular data, right? Like the Titanic data or breast cancer data. You have few samples, few covariates, not gigantic data set. So these are the methods of choice. Oftentimes it's hard to beat them. Also, like logistic, like kernel SVM, for example, like kernel SVM or something like that, they're very close. And then there are some simpler parametric generative models that we haven't talked about. Fisher, linear discriminant analysis, naive Bayes. You can figure that out. These are like basically model that's basically, remember P0 and P1 we had. So they model these probability under class 1 and class 0 using some simple parametric models. And then you have, when you write down the optimal rule, you get some nice closed forms. Okay, so things we haven't covered, things we hope to cover is this one. So have people seen language models? What are language models? So I guess you've experienced like working like or interacting with ChatGPT or these recent chatbots. So there are language models, they're sort of generate text or language, like material. So you input something and then they, what they do is really like try to complete what you write. So if you write a question, the answer is part of the rest of the flow of text. So they try to predict, basically what effectively they're doing is predict the next word. And it's really, or the next token, maybe not exactly the next word, but the next token, which you can think of it as the next word. So when I say something, you can think of it, me as sort of trying to like put words together, right? One word after another. If I can know what the next word is after all I've said and done, so that word I put there, now I'm going to predict what the word after that should be and so on. Just predict the next word sequentially, and you'd have like text. And this seems to be like very simplistic, but this apparently works if you train it on very large amount of data sets and if your model is pretty complicated. So the idea that these models are generative, so they generate data, but it's like you want to put like a distribution on language and like sample from language, different kind of text. And the way that they do it is by turning it into a prediction problem. So we've seen prediction problem as the main topic, like we talked about, like supervised learning, sometimes called, but prediction is better. So language generation, language modeling can be like recast as a prediction problem. So you have a chunk of text, like these are words, one, like the first word, second word, third word, t-1 and t, okay? So if I try to predict, so let's say I've seen this part, and if I can predict that one, I can put it there. Then in the next step, I have everything up to this. Now I'm going to predict the word after that and so on. Okay. So the problem is really predicting, given this part, what comes next. So you can call this X, this Y. This is our usual prediction problem. Okay. And it's actually very similar to the very early prediction problems that we look at, because words are discrete. So X is going to be discrete. It's not going to be binary. So let's say, so the words in like a language are, there are a lot of words, but let's say there are a few letters. So let's say 26 letter or something. And then like uppercase letters, lowercase letters, and punctuations, let's say have 26 times 2 plus like 12 punctuation marks. Let's say if I treat prediction as predicting the next character, I can just work with 64 characters. So if these words are really characters, it's enough to assume that this has 64 levels. This guy would have 64 times 64 times 64. So it would be 64 to the t. So if we call this C, so C would have this, like Y would have this many levels. This guy would have C to the power t levels. Okay, 64, let's say 8, for example, t is 8. That many choices. In practice, that's not what they do, but the code I'm going to go over is actually written in this way. It's like an exercise done using characters, just creating characters. You can do substrings and so on. So these are called tokens. So at what level you tokenize, that's the pair. It depends. So you can tokenize at the level of words, at the level of characters, at somewhere in between. So I guess the OpenAI's version is somewhere in between. So some of it is open source. They used to be open source. And then, but it doesn't matter for us. So it's just the fact that it's discrete objects. So the classification problem would be a multi-class classification with that many levels. So just let's focus on this case. Let's say I have 64 letters that I'm going to try to predict. I have this is going to be the levels of my features. Features is also like discrete, but it has this many levels. And if you recall, for example, in the Titanic case, we had a binary vector, and like a binary feature, it had two cases. Or we had like a binary feature and ternary feature, it would like they interact to produce like a 6-level feature. So here you'd have like a discrete feature with this many levels, 64 to the 8. Let's say if my another name for this is a context. So if my context is t here is like 8, how many words I want to look back to predict the next word? So t like context length. But that's basically it. It's a very simple prediction problem. Discrete covariate, so you can think of it as just the entire thing as one discrete covariate with this many levels. What I want to predict is also discrete, very simple. What is the difficulty? The difficulty is like there are too many choices. So if I want to try to, for example, estimate this conditional distribution, that's what we care about. Based on this, you can do like the optimal rule. I can try to estimate basically this probability mass function. So x is like these, and I have to estimate this. This will have c to the t plus 1 parameters. Basically, each one of these probabilities for different choices of this would be one parameter that I have to estimate. I have to estimate this entire distribution. Question? Do you have any questions? No. Okay. Another way to look at this problem is if I look at the decision rules. Okay, so if I want to like once I have that probability, I can like find the optimal rule which maximizes the, remember like you take the argmax over WT. So if you give me this, I'll take the argmax whenever I estimate this, I'll take the argmax over this, and that's my rule. If you look at those rules, the number of those functions is going to be this many. It's like how many basically the alphabet size for y is to the power of the alphabet size of x. I'll let you think about this yourself. And this would be c to the power c to the power t. So that would be like this, 60 to the power 64 to the power 8. And if you do it in R, it would be infinite. So it can't be computed. It's like 10 to the power of 10 to the like 15 or 14. It's like 10 and then this many zeros. So that are that many functions that you have to search over. So that's the complication of the problem. So if you want to think about how complicated the problem is, it's compare this to the case where we had like this was sex, this was like survived. So 0, 1, 0, 1. There are 4 binary functions. So how should I decide here? How should I decide here? How should I decide? So 2 to the basically 2 to the 2 here would be the number of binary functions. The other one would be 2 to the 6. One of the things in decision theory that we did, you're basically choosing between that many. Sorry, in this case, it would be like under 0, either I'm 0 or 1, either one, I'm 0 or 1. So there are 4 choices. There is 2 to the 6. Here is like 10 to the 14 cases. Okay, so you have to somehow reduce this complexity. That's the difficulty. So far, so good. There's a prediction problem, discrete prediction problem, but the parameter space or the space of possibilities is too big without any constraints. So far, so good. So what is some idea that, how can we do this? How can I restrict? Like anyone has an idea, just quickly. How can I restrict this class of possibility? What do you think just a little bit? There's a very simple solution here. It's not going to work that well, but yeah.
How did you get the 64 to the 64 to the
8?
Sorry, could you just say that again?
Yeah, anyone can argue that. So suppose I'm like predicting a response, like x, like I want to learn a function from x to y. Okay, this is the number of levels of x. This is the number of levels of y. How many possible functions do I have? All right. So here, this would be like c, which is c to the t, because that are that many. This is the size of how many. So I have 64 choices here, 64 choices up to 64. Right, so it would be like C to the power T.
Is it because the amount of words you're looking at previously is 64?
That's like 64 to the 8. That's this part. The amount of words that I'm gonna predict next is 64, which is C. But the number of functions here is, for each one of these, I have this many choices, right? So you can imagine a table that has C to the T possibilities. Like you have to rearrange this in scikit-10. So each one of these is one possibility of the previous cases. And for each one, I have now like 64 choices for the output, right? So you have this many choices, and they're like this many locations. For each location, you have to pick one of these levels, and all of it is possible. So for each one of these possible so each one is like a possible sequence of passwords. Right? For each one, I should choose the next word, right? And I can choose any way I want. And I can fill this table any way I want. And for each one, I have this many, like 64, 64, 64, and there are this many, like there are 64 to the 8 possible like holes that I have to fill, and each one has this many. So I get this to the power this. 64 to the 64 to the 8. There are this many holes and this many choices for each hole.
So if your context was only the previous word, then you reduce the space.
Great. That's exactly the solution. So if my context, so if I just look at everything in the past and I say I'm just gonna look at this guy, right? I'm just gonna predict the next word based on just the last word. Then I would reduce this complexity by a lot. So how much complexity would I have then?
Just 64 to the 8.
64 to the 8 is like, the context here is just this, right? So there's just one 64 possibility here, right? So this word, it takes 64 choices. I don't care about the rest. There's no 64 to the 8, just 64 to the 1. That's this many, and then I have how many choices I have for so it would be big. If I'm not wrong, 64 to the 64. But actually, okay, so maybe this calculation is a little bit too pessimistic, but just focusing on this guy, right? The number of parameters, so if you look at the number of parameters, I don't have to worry about the like the decision rules. The number of parameters would just reduce from this to this much, okay? So we just C to the 2, which is like 64 by 64. Right, that would simplify the problem a lot. So in terms of parameters, this is going to be like 64 to the say T, okay, yeah. Yeah, so 64 to like 9 here, but here it will be 64 to the 2. So that would reduce the problem a lot. So that's the idea of the Bigram language model. So what they do, they assume that the present only depends on the immediate past. And so if you think about so why this makes sense, because in general you can write, let's say I can write any joint distribution by factorizing recursively. So I can, like, if you have like P W0, W1, W2, you can write it as P W2 given W1 and W0 times P W1 given W0 times P W0. That you can sort of verify. It's not difficult. And then what you're doing is that you're saying, for example, this doesn't depend on W0. Once I condition W1, it just like that. It's like that. And so if you write this down, it would look like this. It's just going to be a product of these pairs of words. So this is called a Bigram model. because these pairs are bigrams. So these are like the words that immediately follow each other. So if you look at the text, if you like look at the pairs of words that appear together, these are called bigrams. If I do like that would be like t gram or t plus 1 gram. If I look at like this context, if I have 3, it would be 3 gram and n gram. So the bigram is the smallest besides just looking at single words. So if I do that, and there is a bit of more complexity here because in the language, as I vary t, this could change. Still, like it could depend on my position. So for example, if I'm looking at, I can reduce the thing, but it could be like at the start of a sentence, these probabilities are different at the end. So where I'm in the sequence, it might matter. But in the bigram case, you also ignore that. You assume that this is like constant as a function of t, the invariant to t, okay? Then you really have like a 64 by 64 matrix. So I just have to specify what is the probability of observing any of the 60 word that comes next, given any of the previous 60 words. So you can like encode this by a matrix, basically. So the probability WT plus 1 goes here, this goes there, and this would be that probability, the probability of, which I'm going to write as well as like WT. So this is like pi ij, something like that. So it's a matrix indexed by 2 entries. And now you really have a very small parameter space. Okay. Does that sound good? So if you believe that, then you can write it like that. Or instead of probabilities, I can work with logits. So you can think of another matrix, which is real value. So this is 0, 1 value. So in 0, 1 to the C times C. Oh, sorry. Okay. This is okay. So let me show you what this is. So this is like I have a table. Each row would be a probability distribution. Okay, so that's going to be the probability that this guy is equal to, let's say, a particular W. Then I have to specify what is the probability next. So for every basically row, I need to specify a probability which tells me what is the, let's call this U. Given that the previous word was U, what is the chance that you observe the next word being V? Okay, so rows have to be probabilities. And these are sometimes called embeddings. So you can think of it as you're embedding words into a real valued space. And now I can compute with them, basically. So words are discrete, but this probability basically is going to be a representation of this word. So some words have a particular pattern. For example, if it's like, I don't know, I, maybe the next word is like the next letter is always E or something like that. So this position is going to be very like for E would be very highly, the value would be high, the rest would be maybe smaller. But this vector is like a signature of that word as far as the probability of the next word is coming. So that you can think of as embedding. And this idea of embedding things in real spaces, like real value spaces, is like prevalent in sort of deep learning and also machine learning. So that gives you an embedding. So this is an embedding table. And alternatively, I can look at logits. So instead of looking at probability vector, it's easier to like look at theta, I write it as U star. So, and then pass it through a softmax operation to get the probability. So this pi of U star, this is like pi of U star, that row is like the softmax of theta U star. And now this is really like a free embedding, so it just can be anything. So I'm embedding words in reals. So this is going to be in RC. So like a 64-dimensional real space. So each word is going to be here, and what it means is that if I pass it through a softmax, that's the probability of what the next word is going to be. So that gives you a very nice interpretation. So far, so good. So we have about like 20 minutes to fill the dots to GPT. So this one you can fit using what you know. the idea is, how do we train? It's like a parameter space is like this capital theta now, if you want, like 64 by 64. And we can write down the likelihood, everything works fine. The only thing is I have to specify how we actually gather training data. So the idea is that this is at the population level. This is one particular sequence of words. In practice, you observe like many chunks. So these blocks or context vectors. So you're going to subsample, like sample from a text randomly, these like pieces of 8 words or 9 words. Randomly you pick them, and each one would constitute one training example. So I'm gonna like have my text. I'm gonna like go pick these pieces of words. This last one is gonna be my Y. This one is gonna be my X. Next time I'm gonna pick this part. This one is gonna be my Y that I'm gonna predict. This is gonna be my X. Maybe sometimes I might like have overlapping pieces. I might pick this one. And then it's fine. So randomly pick. Because of these overlapping things, things might not necessarily be independent, but we treat them as independent. So assume that these are independent draws from this model. This is very similar to an idea in statistics, which is called pseudo likelihood. So you don't have a perfect likelihood, but you just pretend that things are independent and you write down the likelihood, it would be a pseudo likelihood. So here's going to be my training. W subscript I is like the ith sample, and then this is like the words that I see in that context or like that chunk. And then you can write down the pseudo likelihood or treating them as independent. So I have n samples. This is the Bigram model for each one, and then you just plug in. So if you, for simplicity, call the previous word the xit to be like closer to our notation, yit for this last one. You write things down, it would be like this log softmax, it's like the cross entropy. So you write down the likelihood, it's very easy. And you can also write it in terms of cross entropy. So this you can easily like implement in PyTorch. And that would be a Bigram model. So the end result is that you're going to get this theta matrix. And whenever you're going to generate the tag, whatever you have seen so far, you're going to go look at the last word that you saw, and then you can read off the probabilities. So this would be like S of theta U star. If U is the last word, this is going to be the probabilities of your next word, and then you like draw from a multinomial or categorical with that probability. You fill in that word. Now that's the last word. You're going to predict the next one based on your own prediction now. Okay, just to continue sequentially and in generate things. This is obviously not going to work that well, but it does produce some interesting things. So if you get to it, I'll show you like the code that I'm going to like try to explain. And that's written to predict like a text written by like Shakespeare. And you can see like punctuation marks like start to like be okay. So if you just randomly generate words, it doesn't look like text. But if you do this, it looks like you have like some words and some spaces and like some like new lines and stuff. There are no like meaningful words, but it looks a little bit like text. So far, so good. Okay, that's the first step. That's the first step of the language modeling. And you already can like do a little bit of prediction, not a GPT level prediction, but questions? So how do we extend? Obviously, we have to like dispense with this simplified assumption. So we can't just predict based on the previous word because the words before it also are meaningful. So I want to use the entire context, and then I can like also increase. So if you like look into the GPT, so you can see the context like is increased like from iteration to iteration. So, well, let's say 8 or like whatever, maybe 32,000, whatever I want to pick. I have to have a way of like making these communicate with each other. So I have to be able to like sort of what the idea is to try to make these embeddings communicate with each other, sort of this word also knows about the embedding of this, maybe updates its own embedding based on the previous words. So we're still going to have some embedding of some sort, but it's not going to be just the probability of the next word. It's going to be a little more complicated, a little bit more latent inside, and like the deeper behind the scenes. And these embeddings sort of talk to each other, and then eventually you get a probability. Okay, so that's the main like paper that I want to maybe discuss in the remaining sort of 15 minutes. So this is the one that started the business of GPT. So this is the transformer paper. So they proposed this transformer architecture, and that's what I'm going to try to do. So this is saying attention is all you need. And the idea is that the previous models had these recurrent neural networks or convolutional neural networks for text, and they were complicated, and they're proposing a simple network architecture that sort of like actually beats them as well. So simple, easier to understand, easier to train. Actually, so this is for machine translation. But what we're doing is going to use half of it. So that's basically their model. And I'm going to try to explain. So this part is like an encoder. This part is a decoder. So we're going to just focus on this decoder part. So decoder is enough for us because we're not doing translation. And this is called decoder only transformer. And this already performs very well. So just ignore the left half. So this is some sort of like cryptic architecture. And I'm going to try to parse it a little bit. So what happens is that these are sort of the embeddings that we start with. So it used to be our embeddings are sort of like probabilities of the next word or the logics of the next word. But you can now imagine that I sort of get like maybe like at some point I got some embedding of words. Maybe it's like simple as we talked about. The idea is that in addition to the embeddings of the words, I also need to embed the position. So what one of the like interesting ideas is I'm gonna like have like an embedding table. So this is like word U, and this is gonna be an embedding for the position where in the sequence I am. Okay, so if I'm in the sequence, like the first in the like, if you look at the context, if I'm here, that position would have an embedding as well. So the position itself is embedded into the space in which the words are embedded. So this is a word embedded, let's say in R to the now let's say D. This is embedded in R to the D as well. And then these are going to interact. So the way that they do it is actually like if this is like X. So for any word, so you have like and then let's say embedding 1, E1 of WT. This is E2 of WT. So this only depends on the T. This only depends on the word. So you just add these two embeddings because they're vectors. So you do the addition. So the embedding for that word would be a part that just depends on the word itself, and a part that depends on the position. And that would be the vector X. So let's not worry too much about this. It's not that hard. But for each word in the context, we get an embedding vector that we want to learn. We want to learn it just encodes both the word that it contains and the position. It's like addition of those. It's a little bit weird. So you imagine that you concatenate these, but that's how they do it. And it seems to work. So this in this final embedding contains like the embedding sort of has information both from the position in the context and the word. Then there is this interesting idea of mask multi-headed attention that I want to talk about. And this part you don't need because we're not doing the encoder. Feed-forward network is one of these feed-forward networks that we have seen, like multi-layer perceptron. In fact, it's like a 2-layer thing. And then here, and then times n. So this they repeat it n times. So this is one block, and then they compose it with the same block of X, a block similar to this, and another block similar to this, and they go deep. Okay, that's the deep learning part. So times n means like just concatenate that n and sequential. Okay. And then the final layer, you have the linear, it's like one of these linear layers that you've seen, and the softmax of the probability. So everything should be sort of clear once this part is clear. And also this layer is clear. And also this is another innovation in deep learning that people are using. So I'm going to try to explain this in the remaining part. So this masked multi-hit attention is the multiple of these attention blocks. So let me show you what this is. So the attention block is the one that I want to focus on because that's what we talked about. So if you recall local averaging, okay, the idea of local averaging was very simple. So you had like xi's, you have yi's, and you have a test point. And this was our regression function. The way we constructed it, you measure the similarity of your test point to your training data, and then you average based on this weight the corresponding responses. So in the kind of these transformer sort of literature, let's call the xi key and yi's value. They think of it as like a database of information. So if I have the key, I'm going to look up the value, which is the response. And then for this as a query, you can think of it, the query comes in, you're going to like match it to a key, but I compare it to different keys, and then you average the values. Okay, that's the language that they're using. So key values queried, and then you call this like K, this is going to be V, and this is going to be Q. The other interesting part is that because this procedure is going to happen on these positions, or the encodings, not positions, the encodings, I can have the query to also be real, like vector value. Sorry, these are going to be vector value, and this is also going to be vector. So usually for us, this is like a label, but this value can also be vector value, and so it can contain sort of more information. So with these namings, so what happens is this index I is going to be like T for us. So now this would be XT. That would be the position. Actually, I'm going to call it KT. So that would be KT, not XT. That would be VT. And then I have, so YI would be VT value. This would be key. And then X is mapped to Q. Q is going to be the query. So query comes in, I compare it with the key, and I average the values. This is our local averaging. This used to be YI. So now everything is on T. And these weights, the way that they construct, this kernel is just a simple exponential inner product of the key times Q. So we haven't seen this. This is very close to the Gaussian. They do it because instead of doing something like that, because the inner products are easier. They also have a scaling, but I'm not showing the scaling that can be absorbed. But with this kernel, that is sort of the idea of attention. So they call it the attention, but it's really local average. So I have these vector values that I average based on the similarity of my query to the key, and measure the similarity like this. And if you plug this exponential here, you can see that this way looks like a softmax business. So you can actually do this by a softmax operation. The main point, however, so this part should be familiar to people. So this is very similar to our local averaging. The part that's interesting is this idea of self-attention. How do I get this key value, the key value pairs, and also the query? So in this idea of self-attention, all of them are generated from the data itself. So each one of these words, remember this has this embedding, it's going to pass this through linear functions. So like linear models that we have seen, like NN linear if you want. It passes through one linear model, produces the key. It also passes through another linear model, produces this is the query set, query, key, and the value as well. Okay, these are all linear. So each word at every position is gonna like produce these queries and keys and values. And not everyone has one of these. They have one query, so what it cares about, let's say, it has a key and it also has a value, shares the keys and values among each other. So they form this. Everyone calculates this for the query of itself. So I have my own query, I plug it in, the keys are coming from everywhere else, and the values are coming, and I calculate it, and I get sort of an update. Okay, so this quantity would be like the update of that attention. So that would be a more updated like embedding. And so basically these two ideas together sort of form the basis of that multi-headed attention. So every embedding, every word in every position creates all these three values by passing its own embedding through these linear layers. And once you pass it through these linear layers, I feed it to that attention block, which is just basically Nadari-Watts or like the local averaging. So I'm locally averaging all the other values of other guys by comparing my own query to the keys of everyone else. Okay, so this all happens on the context, not on the like samples. And so to combining these two ideas, you would get this kind of yeah. So this is not a good representation, but you get this head. This they call it the head. Attention head does this, and you do it multiple times. So so each one of these is this. So like linear. So this is sort of but what they don't show here is basically like a single thing goes there. So a single thing goes and then produces these and then values, keys, and queries. And then you do it in parallel multiple times and then concatenate them. That would be your final representation. And then you also, for whatever reason, you pass it through a linear layer as well. So you mix everything again. So linear like maps sort of mix everything. But that's the idea of sort of one attention head, multiple attention head just does this multiple times in parallel. And then you concatenate the resulting vector. So one embedding goes in, each one of these produces another embedding, and you concatenate these embeddings together, you get a new embedding. So this new embedding now like mixes everything up. The original sort of positions were like just ignoring everyone, each other, but now we use like sort of this nonlinear sharing of information. That's this part. The other part's really not that. So this is the key idea. The other parts are like innovation. So this is a skip connection. This is called sometimes a residual net. So you add your input to also the output as well. This improves this is called residual or skip connection. There's a paper, they call these res nets, very popular, or skip connection. This improves the optimization. This is layer normalization, which is another sort of trick to improve optimization. But this skip connection and layer normalization is just like simple ideas. The main idea is this. And the masked part is, I just want to talk to the guys that are before me. So I'm going to mask the information here. I'm going to just average over everyone that's before me. I'm not going to use the information of the words that are after me. If you don't do it, you lose the causality sort of. You're looking ahead. So that's the mask part. But the rest is sort of really just repeating this procedure. Okay, so there is this local averaging Nadari-Watson type thing, but not with the translation layer kernel, with a dot product kernel. You do it in parallel. You concatenate things, and an embedding goes in, which has two parts. One based on the word, based on the position, and then this part is really the one that sort of mixes everything up. And then the feed forward part is sort of the computation, basically, a little bit of computation. And the feed forward network is very simple. You can see it here. They have it here. Yeah, so it's just like a two-layer neural net. One layer, and then the last layer is just one really nonlinear layer, and then one linear layer. Very simple. So this part is really simple. This is obvious, sort of. The only trick is this part, and sort of you sort of understand this as well. So I'm going to post like a GitHub repository. Someone wrote a very like short version. They implemented a short version of this in PyTorch that you can read. And also there's an accompanying YouTube video that they explain it very well. And you should be able to play with it. But hopefully it gives you an idea. These are not very complicated like model to understand. They're difficult to scale. So once you add this, like start to concatenate these blocks like sequentially, then it's harder to optimize. And all sorts of tricks goes into that. And like if you scale it, you get like GPT-1, 2. And then GPT-3, 4, they use other stuff like reinforcement learning and things that I don't know about. But this is the basic idea. So this has like scaling this to like big data sets, training it on like billions of tokens, like to these things that look like they actually learned something from the data. Sounds good. Okay, unfortunately, we don't have that much time to go further, but it's a good time to stop, I guess. And any questions? Okay, then thank you guys. It was great pleasure to teach here, and hopefully to see you around, maybe different courses later. And good luck on the final exam. Okay.